All right, we're back. Guess who's back? Back again. Guess who's back? Pop out that chat. Copy link. All right, I think we got live. Live. What's going on? Let's say, yo. Yes, working. Yeah, good. Let's go. All right. We're live. We live. Let's go let people know in the Discord what's up. We live. Alrighty. Let's get some things kind of set up here. There you go, docs, chat. Alright. Get that going. Okay. Alright. Early stream this morning. Let's see who's awake. Who's up? Who's awake? Nobody's in here so far. It's dead. Nobody's awake. Yeah, okay. Let's see who's awake. Woo! Reporting. We'll let some people roll in here for a couple minutes. Woohoo! It's dead in here. Let's just go ahead and get started. Oh well. It's fine. Okay. Hello, everybody. You go ahead, and I'm also going to record for today as well. You go like this. That's fine. Okay. I think we're okay. Maybe I'll make it a little bit bigger. All right. Let's go ahead and get started. All right, everybody, welcome back into the stream and back to the channel. My name is Michael. Hope you're having a wonderful day so far. Today, we're going to be starting a new series on the channel. We're going to be starting this book that I've been wanting to read, the Corman Introduction to Algorithms. It's a book written by the MIT staff to kind of go over their algorithm course, but provide the details that they were wanting to provide on a more, elementary level for kind of all readers, but provide the meat and potatoes that is necessary to actually, understand these algorithms, hopefully, and, progress. So I'm really excited to get into this book and get going here. We're hoping to finish up chapter 1 this stream, and then we'll continue on in some future streams and videos. So this is also going to be a watch along. I am recording, so hello to you guys on the YouTube channel for the videos. We will be doing a watch along or read aloud series where you can keep up with me as I read through the book and take notes. You can access these notes on my GitHub, linked down in the description. But without further ado, let's go ahead and get started getting into this book. So this is Introduction to Algorithms, 3rd edition by Corman and some other people involved at MIT, more specifically, in 2009, MIT, Massachusetts Institute of Technology. Cool. Let's go ahead and get started here. I'm excited. I've kind of already browsed through the preface and the introduction here. It's kind of just some stuff that's not really super prevalent to the content here, so we'll go ahead and get started. It's more mainly like thank yous and notes. All right, chapter 1. I'm gonna do my best to read here, so sorry if I mess up a couple times. I ain't no pro. Chapter 1, the role of algorithms in computing. What are algorithms? Why is the study of algorithms worthwhile? Let me know also how my my mic is, if you want me to turn it up or turn it down. What is the role of algorithms relative to other technologies used in computers? In this chapter, we will answer these questions. 1.1 Algorithms. Informally, an algorithm is any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. I'm going to take that right here. I'm going to say algorithm. Right, any well-defined computational procedure that takes some value or set of values as input and produces some value or set of values as output. Fair enough? Cool. An algorithm is thus a sequence of computational steps that transform the input into the output. We can also view an algorithm as a tool for solving a well-specified computational problem. Okay. The statement of the problem specifies in general terms the desired input/output relationship. The algorithm describes a specific computational procedure for achieving that input-output relationship. For example, we might need to sort a sequence of numbers into non-decreasing order or increasing order. This problem arises frequently in practice and provides fertile ground for introducing many standard design techniques and analysis tools. Here's how we formally define the sorting problem. Input is a sequence of n numbers, a1, a2, all the way up to some number of a sub n, right? And output is a permutation or reordering of the set of numbers, sequence of n numbers, where you have a prime, a sub 1, a prime sub 2, all the way to a prime sub n, where I'm guessing that these are just, a prime is the reordering of these sequence, right? Whereas a prime is less than a prime sub 1 is less than a prime sub 2, which is less than, all the way up to a sub prime n, yeah. For example, given this input sequence 31, 41, 59, 26, 41, and 58, a sorting algorithm returns an output sequence of them in sorted order. Such an input sequence is called an instance of the sorting problem. Okay, so an instance here. An instance. What is an instance, right? Such an input sequence is called an instance of the sorting algorithm. An input to an algorithm, right? So, for example, in general, an instance of a problem consists of the input satisfying whatever constraints are composed of the problem statement needed to compute the solution of the problem. Yeah, that's a good way of saying it right there. I like that. I'm going to take it right from the book. The input satisfying whatever constraints are composed in the problem statement needed to compute a solution to the problem is an instance, right? Because many programs use it as an intermediate step, sorting is a fundamental operation in computer science. As a result, we have a large number of good sorting algorithms at our disposal. Which algorithm is best for a given application depends on, among other factors, the number of items to be sorted, the extent to which the items are already somewhat sorted, possible restrictions on the item values, the architecture of the computer, and the kind of storage devices to be used, main, memory, disks, or even tapes. An algorithm is said to be correct if, for every input instance, it halts the correct output. Okay, so we have a correct algorithm, right? An algorithm is said to be correct for every input instance. For every input instance, it halts with the correct output. We say that a correct algorithm solves the given computational problem. An incorrect algorithm might not halt at all on some input instances, or it might halt with an incorrect answer. Contrary to what you might expect, incorrect algorithms can sometimes be useful. If we can control their error rate, we shall see an example of an algorithm with a controllable error rate in Chapter 31 when we study algorithms for finding large prime numbers. Ordinarily, however, we shall be concerned only with correct algorithms. An algorithm can be specified in English as a computer program or even as a hardware design. The only requirement is that the specification must provide a precise description of the computational procedure to be followed. What kinds of problems are solved by algorithms? Sorting is by no means the only computational problem for which algorithms have been developed. You probably suspected as much when you saw the size of the book. Practical applications for algorithms are ubiquitous and include the following examples. The Human Genome Project has made great progress toward the goal of identifying all the 100,000 genes in the human DNA, determining the sequences of the 3 billion chemical base pairs that make up the human DNA, storing this information in databases, and developing tools for data analysis. Each of these steps requires sophisticated algorithms, although solutions to the various problems involved are beyond the scope of this book. Many methods to solve these biological problems use ideas from several of the chapters in this book. thereby enabling scientists to accomplish tasks while using resources efficiently. The savings are in time, both human and machine, and in money as more information can be extracted from laboratory techniques. The internet enables people all around the world to quickly access and retrieve large amounts of information. With the aid of clever algorithms, sites on the internet are able to manage and manipulate this large volume of data. Examples of problems that make essential use of algorithms include finding good routes which the data will travel. Techniques for solving such problems appear in Chapter 24, and using a search engine to quickly find pages on which particular information resides. Related techniques are in Chapter 11 and 32. Electronic commerce, e-commerce, enables goods and services to be negotiated and exchanged electronically, and it depends on the privacy of personal information as a credit card numbers, passwords, and bank statements. The core technologies used in electronic commerce include public key cryptography and digital signatures, covered in Chapter 31, which are based on numerical algorithms and number theory. Manufacturing and other commercial enterprises often need to allocate scarce resources in the most beneficial way. An oil company may wish to know where to place its wells in order to maximize its expected profit. A political candidate may want to determine where to spend money buying campaign advertising in order to maximize the chances of winning an election. An airline may wish to assign crews to flights in the least expensive way possible, making sure that each flight is covered and that the government regulations regarding crew scheduling are met. An internet service provider may wish to determine where to place additional resources in order to serve its customers more effectively. All of these are examples of problems that can be solved using linear programming, which we shall study in Chapter 29. Although some of the details of these examples are beyond the scope of this book, we do give underlying techniques that apply to these problems and problem areas. We also show how to solve many specific problems, including the following. We are given a roadmap on which the distance between each pair of adjacent intersections is marked. We wish to determine the shortest route from one intersection to another. The number of possible routes can be huge, even if we disallow routes that cross over themselves. However, how do we choose which of all possible routes is the shortest? Here we model the roadmap, which is itself a model of actual roads, as a graph, which we will meet in Part 6 and Appendix B. And we wish to find the shortest path from one vertex to another in the graph. We shall see how to solve this problem efficiently on Chapter 24. Don't get too caught up in kind of these examples here, as they're kind of just kind of preludes, precursors, and kind of foreshadowing to what's coming in the future chapters. This is kind of like an introduction in the roles that algorithms can play into solving these kinds of problems to kind of pique your interests. And so, yeah, don't really get too caught up in these examples right now, as it kind of can be kind of daunting, for sure. We are given two ordered sequences of symbols. X equals to a sequence of x1, x2, all the way up to xm, and y of the same sequence all the way to y sub n. And we wish to find the longest common subsequence of x and y. A subsequence of x is just x with some or possible all of none, or with some. It's just x with some or possibly all or none of its elements removed, right? It's just a subsequence of a sequence, is a chunk out of it. For example, one subsequence of A, B, C, D, E, F, G would be B, C, E, G. Interesting. B, C, E, G, so that you can skip the D? Pause. The length of the longest common subsequence of x and y gives one measure of how similar these two subsequences are. For example, if the two sequences are base pairs in the DNA strands, then we might consider them similar if they have a long subcommon subsequence. If the sequence X has m symbols and sequence Y has n symbols, then the sequence X and Y have 2 to the power of m and 2 to the power of n possible subsequences, respectively. Selecting all possible subsequences of x and y and matching them could take a prohibitively long time unless m and n are very small. We shall see in Chapter 15 how to use a general technique known as dynamic programming to solve this problem more efficiently. We are given a mechanical design in terms of a library of parts, where each part may include instances of other parts. And we need to list the parts in order so that each part appears before any part that uses it. If the design comprises n parts, then there are n factorial possible orders, where n factorial denotes the factorial function. Because the factorial function grows faster than even an exponential function, we cannot feasibly generate each possible order and then verify that within that order, each part appears before the parts using it, unless we have only a few parts. This problem is an instance of topological sorting, and we'll see an example in chapter 22. And then more points here. We are given n points in the plane, and we wish to find the convex hole of these points. The convex hole is the smallest convex polygon containing the points. Intuitively, we can think of each point as being represented by a nail sticking out of a board. Yeah, the convex hole would be represented by a tight rubber band that surrounds all the nails. Each nail around which the rubber band makes a turn is a vertex of the convex hole. Got you. It's a good way of analogy. Any of the 2 to the power of n subsets of the points might be the vertices of the convex hole. Knowing which points are the vertices of the convex hole is not quite enough either, since we also need to know the order in which they appear. There are many choices, therefore, for the vertices of the convex hole. Chapter 33 gives 2 good methods for finding the convex hole. Okay, so like I said before, don't get too caught up in these examples right now. As you can tell, these are talking about all the way in chapter 22, chapter 33. This is chapter 1, so they're just kind of getting into some examples and what the future might hold for us as we read this book. Yes, these are kind of dense and kind of hard to visualize right now, but I'm sure as we get going, it'll ease up for us. So stay with us, boys. Stay with us. These lists are far from exhaustive, as you have probably surmised from this book's heft, but exhibit two characteristics that are common to many interesting algorithm problems. They have many candidate solutions, the overwhelming majority of which do not solve the problem at hand. Finding one that does, or one that is the quote best, can present quite a challenge. 2, they have practical applications. Of the problems in the above list, finding the shortest path provides the easiest examples. A transportation firm, such as a trucking or railroad company, has a financial interest in finding the shortest paths through a road or railroad network because taking shorter paths result in lower fuel and labor costs, right? Or a routing node on the internet may need to find the shortest path through the network in order to route a message quickly. Or a person wishing to drive from New York to Boston may want to find driving directions from an appropriate website, or she may want to use her GPS while driving. Not every problem solved by algorithms has an easily identified set of candidate solutions. For example, suppose we are given a set of numerical values representing samples of a signal, and we want to compute the discrete Fourier transformation of these samples. The discrete Fourier transformation converts the time domain to the frequency domain, producing a set of numerical coefficients, so that we can determine the strength of various frequencies in the sampled signal. In addition to lying at the heart of signal processing, discrete Fourier transformations have applications in data compression and multiplying large polynomials and integers. Chapter 30 gives an efficient algorithm, the fast Fourier transformation, commonly called the FFT, for this problem, and chapter also sketches out the design of a hardware circuit to compute the FFT. Interesting. So we got a lot of stuff we're going to learn here. Data structures. This book also contains several data structures. Data structures, right? We know what these are, but let's just keep our notes here. A data structure is a way to store and organize data in order to facilitate access and modifications. No single data structure works well for all purposes, so it's important to know the strengths and limitations of several of them. I like that definition. The book gives a good one. What's broke? Let's not fix it. Technique. Although you can use this book as a cookbook for algorithms, you may someday encounter a problem for which you cannot readily find a published algorithm. Many of the exercises and problems in this book, for example, this book will teach you the techniques of algorithms design and analysis so that you can develop algorithms on your own. Show that they give the correct answer and understand their efficiency. Different chapters address different aspects of algorithmic problem solving. Some chapters address specific problems such as finding medians and order statistics in Chapter 9, computing minimum spanning trees in Chapter 23, and determining a minimum flow or maximum flow in a network in Chapter 26. Other chapters address techniques such as divide and conquer in Chapter 4, dynamic programming in Chapter 15, and amortized I can never pronounce this word, and amortized analysis in Chapter 17. Hard problems. Most of this book is about efficient algorithms. Our usual measure of efficiency is speed, i.e., how long an algorithm takes to produce its result. There are some problems, however, for which no efficient solution is known. Chapter 34 studies an interesting subset of these problems, which are known as NP-complete. Why are NP-complete problems interesting? Okay. Although no efficient algorithm for an NP-complete problem has ever been found, nobody has ever proven that an efficient algorithm for one cannot exist. In other words, no one knows whether or not efficient algorithms exist for NP-complete problems. Second, the set of NP-complete problems has the remarkable property that if an efficient algorithm exists for any one of them, then efficient algorithms exist for all of them. This relationship among the NP-complete problems makes the lack of efficient solutions all that more tantalizing. Third, several NP-complete problems are similar, but not identical, to problems for which we do know the efficient algorithms. Computer scientists are intrigued by how a small change to the problem statement can cause a big change to the efficiency of the best known algorithm. You should know about NP-complete problems because some of them arise surprisingly often in real applications. If you are called upon to produce an efficient algorithm for an NP-complete problem, you are likely to spend a lot of time in a fruitless search. If you can show that the problem is NP-complete, you can instead spend your time developing an efficient algorithm that gives a good but not the best possible solution. As a concrete example, consider the a delivery company with a central depot. Each day, it loads up each delivery truck at the depot and sends it around to deliver goods to several addresses, right? Like Amazon or something. At the end of the day, each truck must end up back at the depot so that it's ready to be loaded for the next day. To reduce costs, the company wants to select an order of delivery stops that yield the lowest overall distance traveled by each truck. This problem is well known the traveling salesman problem, and it is NP complete. It has no known efficient algorithm. Under certain assumptions, however, we know of efficient algorithms that give an overall distance which is not too far from the smallest possible, or too far above the smallest possible. Chapter 35 discusses such approximation algorithms. Interesting. So this NP complete is there are some problems, however, for which no known efficient algorithms. So I'll just write down that definition. So NP complete problems are problems for which no known efficient solution is known. Problems for which no efficient solution is known. Right? Interesting. Okay, let's keep going here. How's it going? SAQ, what's going on? Hey, Legal. Appreciate you guys for joining me here. Let me get a little drink of water. Hey, we hit 2,900 on YouTube. Thanks so much for the subs, you guys. We're chugging along, almost to 3K. Man, Rita makes you parched. Parallelism. Okay, let's write this down. Parallelism. For many years, we could count on processor clock speeds increasing at a steady rate. Physical limitations present a fundamental roadblock to ever-increasing clock speeds. However, because power densities increases superlinearly with clock speed, chips run the risk of melting once their clock speeds become high enough. In order to perform more computations per second, therefore, chips are being designed to contain not just one, but several processing cores. We can liken these multi-core computers to several sequential computers on a single chip. In other words, they are a type of parallel computer. In order to elicit the best performance from multi-core computers, we need to design algorithms with parallelism in mind. Chapter 27 represents a model for multi-threaded algorithms which takes advantage of multiple cores. This model has advantages from a theoretical standpoint, and it forms a basis of several successful computer programs, including a championship chess program. Okay, interesting. So, physical limitations present a fundamental roadblock to ever-increasing clock speeds. So you can't just keep increasing the clock speeds of chips because of physical limitations. Because power densities increase superlinearly with clock speeds. Okay, so I'm going to get a little bit more information about this section here. Can you break this down a little more? For many years, computer chips got faster mainly by increasing the clock speeds. Clock speed equals how many instructions per second a processor can execute. Okay? Higher clock speeds equals faster programs. The problem with clock speeds is pushing clock speeds higher makes the chips consume more power. Power consumption grows faster than superlinearly with clock speed. So it grows faster than linearly, okay, superlinearly. Example, if double the clock speed, the power needed more than doubles. Okay, got you. So it just says that like it could be exponentially, it just grows at a rate that is greater than linearly, like a 1-to-1, right? With clock speed, with consumption. At some point, chips would literally overheat or melt if we just keep raising speeds. The new solution, multiple cores. Instead of one super fast processor, chips are now built with several smaller processors on the same chip. These are called cores. Each core is like a separate little CPU, and they live on one chip. This approach is called multi-core computing. Yeah, we know about this. Parallelism. With multiple cores, we can now do multiple things at the same time. This is called parallel computing. It's just like our async functions we wrote for our parser script. Imagine instead of one person writing an essay, you now have 4 people writing a section at once. It's faster overall. The challenge to take a full advantage of multiple cores when you write programs or algorithms that are parallel. A normal algorithm might only work step by step, sequential. A parallel algorithm splits the work into tasks that can run simultaneously on different cores. Multi-threaded algorithms. A thread is like a lightweight process, a unit of execution. A multi-threaded algorithm is designed so parts of the work can be done in separate threads at the same time. Chapter 27 from your book gives a model for designing such algorithms. Got you. So we'll say modern processors contain cores which work in parallel to complete work I can never spell this word. Simultaneously. I think. Let's ask it to expand. Can you expand? Oh no, so just, let me look up. I did spell it right. Let's go. Nice. So computers, they parallel computer listed best performance. So I'll say um, when used, we can kind of processor clock speeds increasing at a steady rate. Got you. Okay. All right. That was parallelism. So now we have some exercises here. And is that... Okay, we'll come back to these at the end. Algorithms as a technology. Suppose computers were infinitely fast and computer memory was free. Would you have any reason to study algorithms? The answer is yes, if for no other reason than that you would still like to demonstrate that your solution method terminates and does so with the correct answer. If computers were infinitely fast, any correct method for solving a problem would do so. You would probably want your implementation to be within the bounds of good software engineering practice. For example, your implementation should be well designed and documented, but you would most often use whichever method was the easiest to implement. Of course, computers may be fast, but they are not infinitely fast, and memory may be inexpensive, but it's not free. Computing time is therefore a bounded resource, and so is space and memory. You should use these resources wisely, and algorithms that are efficient in terms of time or space will help you do so. Right? Awesome. We're going to start getting into time efficiencies and space efficiencies here of algorithms, which we've learned about in some of our previous books and in our studies. So it'll be a good refresher here. Efficiency. Different algorithms devised to solve the same problem often differ dramatically in their efficiency. These differences can be much more significant than differences due to hardware and software. As an example, in Chapter 2, we will see two algorithms for sorting. The first is known as insertion sort, which takes time roughly equal to some constant times n squared to sort n items, where C1 is a constant that does not depend on n. Right? We know that insertion sort is a exponential function. Or is it exponential function? Sorry. I don't think it's let's look at the time complexity function chart here. Is it quadratic or exponential is the word for it? What's the word for it? Um, One second. Sorry, quadratic. My bad. Yeah, it's a quadratic function with the power of 2 squared, right? Sorry. Quadratic. Exponential is power of n. The second merge sort takes time roughly equal to some constant n times the log of n, where the log of n stands for log base 2 of n, and c2 is another constant that also does not depend on n. Insertion sort typically has a smaller constant factor than merge sort, so that c1 is less than c2. We shall see that the constant factors can have far less of an impact on the running time than the dependence on the input size n. Let's write insertion sort running time as some constant c times n, and merge sort as running time of some constant c2 times n times the log of n, right? Then we see that where insertion sort has a factor of n in its running time, merge sort has a factor of log n, which is much smaller. For example, when n equals 1,000, log n is approximately 10, and when n equals 1,000,000, log n is approximately only 20. Although insertion sort usually runs faster than merge sort for a small input size, once the input size n becomes large enough, merge sort advantage of log n versus n will more than compensate for the difference in constant factors, no matter how much smaller C1 is than C2. There will always be a crossover point beyond which merge sort is faster. For a concrete example, let us pit a faster computer A running an insertion sort against a slower computer B running merge sort. So we know that insertion sort takes quadratic time, whereas merge sort takes log time. So we know that the merge sort is a lot faster than insertion sort for large inputs. So if we have computer A that's running insertion sort and against a slower computer B that's running merge sort, they each must sort an array of 10 million numbers. So even though the computer B, which is slower, is running a faster algorithm here, I bet you it's going to do it faster. Although 10 million numbers might seem like a lot, the numbers are 8-byte integers. If the numbers are 8-byte integers, then the input occupies about 80 megabytes, which fits in the memory of even an inexpensive laptop computer many times over. Suppose that computer A executes 10 billion instructions per second, faster than any single sequential computer at the time of this writing, and computer B executes only 10 million instructions per second. 10 billion, okay, so then 10 million. So that the computer is 1,000 times faster than computer B. To make the difference even more dramatic, suppose that the world's craftiest programmer code insertion sort is in machine language for computer A, and the resulting code and this is getting really dense here. To make the difference even more dramatic, suppose that the world's craftiest programmer codes insertion sort in machine language for computer A, and the resulting code requires 2n² instructions to sort n numbers. Suppose further that an average programmer implements merge sort using high-level language with an inefficient compiler, with the resulting code taking 50 n log n instructions to sort 10 million million numbers. Computer A takes 2 times 10 to the power of 7 squared instructions divided by 10 to the power of 10 instructions per second, which is 20,000 seconds, more than 5.5 hours, while computer B takes less than 20 minutes. By using an algorithm whose running time grows more slowly, even with a poor compiler, computer B runs more than 17 times faster than computer A. The advantage of merge sort is even more pronounced when we sort 100 million numbers, where insertion sort takes more than 23 days. Merge sort takes under 4 hours. In general, as the problem increases, so does the relative advantage of merge sort. Can you imagine waiting 23 days for your algorithm to finish running? Bro. That's crazy. Algorithms and other techniques. The example above shows that we should consider algorithms like computer hardware as a technology. The total system performance depends on choosing efficient algorithms as much as on choosing fast hardware. Just as rapid advances are being made in other computer technologies, they're being made in algorithms as well. You might wonder whether algorithms are truly the important on contemporary computers in light of other advanced technologies such as advanced computer architectures and fabrication technologies, easy to use, intuitive graphical user interfaces, object-oriented systems, integrated web technologies, and fast networking, both wired and wireless. The answer is yes. Although some applications do not explicitly require algorithmic content at the application level, such as simple web-based applications, many do. For example, consider a web-based service that determines how to travel from one location to another. Its implementation will rely on a fast hardware, a graphical user interface, wide area networking, and also possibly on object orientation. However, it would also require algorithms for certain operations such as finding routes, probably using the shortest path algorithm, rendering maps, and interpolating addresses. Moreover, even an application that does not require algorithmic content at the application level relies heavily upon algorithms. Does the application rely on fast hardware? The hardware design used algorithms. What? Does the application rely on fast hardware? The hardware design used algorithms. Oh, used algorithms. Right, so the hardware design used algorithms. Does the application rely on graphical user interfaces? The design of any GUI relies on algorithms. Does the application rely on networking? Routing in networks relies heavily on algorithms. Was the application written in a language other than machine code? Thanks for the follow, Preston. Appreciate you, dude. Does the application rely on networking? Routing in networks relies heavily on algorithms. Was the application written in a language other than machine code? Then it was processed by a compiler, interpreter, or assembler, all of which makes an extensive use of algorithms. I'm going to read this paragraph again because I chopped that one so bad. Moreover, even an application that does not require algorithmic content at the application level relies heavily upon algorithms. Does the application rely on fast hardware? The hardware designed used algorithms. Does the application rely on graphical user interfaces? The design of any GUI relies on algorithms. Does the application rely on networking? Routing in networks relies heavily on algorithms. Was the application written in a language other than machine code? Then it was processed by a compiler, interpreter, or assembler, all of which make extensive use of algorithms. Algorithms are at the core of most technologies used in contemporary computers. Furthermore, with the ever-increasing capacities of computers, we use them to solve larger problems than ever before. As we saw in the above comparison between insertion sort and merge sort, it is at a larger problem size that the differences in efficiency between algorithms become particularly prominent. Having a solid base of algorithmic knowledge and techniques is one characteristic that separates the truly skilled programmers from the novices. With modern computing technology, you can accomplish some tasks without knowing much about algorithms, but with a good background in algorithms, you can do much, much more. Nice. So I believe that is the end of chapter 1. Woo! Hey Preston, sorry dude. Yeah, what's going on? We're reading Introduction to Algorithms by Corman and some other MIT professors. It's going to be a really great read to further dive into more algorithms on a general level rather than just Python based. Kind of seeing how to kind of actually think about algorithms and developing kind of your own, testing them, also giving you the examples you need of these algorithms on a more broad spectrum base of the sorting thing or stuff we need. So we've kind of learned about a lot of these different algorithms just here and there throughout different stuff we've done, but this is going to be a really kind of nice centralized kind of programmer's Bible, I guess. Feels good. Feels good. Okay. So let's go back and maybe do some exercises here. exercises 1.1-1. Okay. All right. 1.1-1. Give a real-world example that requires sorting or a real-world example that requires computing a convex hull. Oh boy. A real-world example that requires sorting. Okay, that's not too hard. Convex hull might be kind of hard. Let's look that one up though. A real-world example that requires sorting is using any filter, using filters on data for web applications and like shopping products. Sorting via size, cost, size, cost, type, color, etc. So let's go up to this convex hull example again and reread that one. I would like to talk about that one again. We are given n points in the plane, and we wish to find the convex hull of these points. The convex hull is the smallest polygon containing the points. Intuitively, we can think about linking each point represented by a nail. Okay, so you have a plane here, which is my whiteboard. If you have a point here, right, you have a point here. Oh my gosh. You have a point here. You have a point here. So the smallest convex hull is just the polygon created, or whatever, the shape created by wrapping a rubber band across each one, and the band wraps around, that's a vertice of the convex hull. Let's talk about convex hull. From my understanding, I'm going to use the TTS here. Let's talk about a convex hull. From my understanding, if we have a plane or a whiteboard and I make some dots on the whiteboard, the convex hull is the shape created, or the smallest shape created that you can make that contains each of the points. So like a pegboard with a rubber band wrapped around the pegs, essentially, or a cork board that has thumbtacks in it, and you have a band around the thumbtacks. Is that similar to what this might be? Very close, but you've actually described the convex hull. Yeah, the convex hull. Okay, exactly what you described with the rubber band around pegs/thumbtacks. It's the smallest convex polygon that contains all of the given points. Think of this as the outer wrapping or boundary of the points. Perfect. And yes, you're describing a pegboard exactly where the convex hull is. So then what could be like a real world example without giving it away. I am trying to think of a real world example. Got it. In a real world analogy, you can reason through without me just dumping a definition. Flock of birds. Imagine tracking each bird's position in the sky. If you draw the smallest bubble around them, okay, it's just islands on a map. Set of islands. If you want to build a fence around it, sprinkles on a cupcake. If you want to drop sprinkles randomly on a frosting, with piece of saran wrap. Okay, I guess, let's say a real world example that requires computing a convex hole would be for like construction, many construction projects, for fencing, or what is it called? It's not prospecting, but it's like land surveying. Is that one? Let's check. Would land survey be a good use? Yes, land surveying is actually a really good world example of a convex hole. You take a GPS measurements of the boundary markers. If you want the minimal convex polygon that encloses all those survey points, that's a convex hole. And surveying for area calculations. Nice. Look at us. Let's go. Okay, let's do here. 1.1-2. Other than speed, what other measures of efficiency might one use in real world setting? Energy. Other than speed, some other measures of efficiency might in the real world are energy consumption. So other than speed, time. Well, speed and time are kind of related, I guess, right? Realism / feasibility. Energy consumption, realism / feasibility. Measures of efficiency. Interesting. Okay, let's go here and say let's discuss some other possible measures. These are two I came up with. Nice. You're thinking broadly about efficiency, not just in terms about speed / time. Other real-world measures of efficiency we can discuss alongside energy consumption and real-world feasibility of cost. Oh, that's right, costs. Costs, that's such an easy one. Pricing. Cost less budget, I guess. Sorry, budgeting. Space, memory. Yeah, right. Space and memory. Scalability, maintainability, sustainability, scale, do you spell scale? Is it, there's an E in scalability? No, yeah, no. Scale ability, maintain ability, etc. Right, what are some longevity, environmental impact, accuracy, flexibility? We'll say flex. It's flexibility with an I. Yeah. Cool. 1.1-3. Select a data structure that you have previously seen and discuss its strengths and limitations. Okay. We'll discuss a data structure. We'll say a. Which one should we do? Just a list? We'll do a let's do a queue. Like you previously seen, discuss its strengths and limitations. Which one should we do? A dictionary. I mean, it's more of like a map, I guess. We could do like a hash map. We could do sets. Let's do a set. Okay, so we'll say pros. We'll say cons. So pros of a set is fast lookup, right? Fast lookup. You have easy insertion or deletion, right? And then you have if needed, right? Unique items. And then some cons would be, right? Now on sets, I forgot, order is unordered. Right, it's unordered. So cons, unordered. Like there's no sorting, so you can't sort a set. Gotta be sorted in place. Right. What are some pros and cons of a set? prevents duplicate values, tracking unique items, efficient operations is finding intersections, O(1) based lookup, maintain element order. No, cannot access by index, right? That's a good one. Hey, what's going on, Yusuf? Or Joseph? That's how I pronounce it. So I'm gonna look up. Let's give it this guy here. Looks like you're starting to break things down into structured pros and cons analysis of data structures. Pros: fast lookup, average case of O(1) membership testing, easy insertion deletion, uniqueness enforced, mathematical set operations. Cons: unordered, no indexing, immutable, or red. Cool. Uh, 1.1-4. How are the shortest path and traveling salesman problems given above similar? How are they different? So the traveling salesman problem. They're both computing shortest paths, right? But the traveling salesman is you've got to come back to the point at some point, right? You find the shortest path, but then you have to come back and refuel or fill up. Whereas the shortest path, you're just going from A to B. It's kind of like a round trip, right? So let's talk. Is the difference between the shortest path algo and the traveling salesman the fact that the shortest path is from A to B with maybe some sub-steps in between, whereas the traveling salesman, a round trip or type where they have to come back to the central depot to refill. Yes, you've got the right intuition. Let's sharpen the distinction a bit. The shortest path goal is to find the minimum of cost between A to B, right? Might just be A to B directly or passing through some intermediate nodes. The real world analogy is Google Maps finding the shortest path from your house to a restaurant. Traveling salesman, the goal is to find the shortest path route that visits every node exactly once and then returns to the starting point round trip. It's not just about finding A to B, it's about covering all locations and ending it back up at the depot. So we'll say the shortest path problem and traveling sales min problems are similar in that they both involve finding optimized paths from location to location, but the traveling salesman problem includes the traveling still requires visits to all locations within the desired destination list and a return back to the starting place or depot. That's a clear and accurate summary. Both deal with finding paths between points that minimize some cost. The difference is the shortest path only cares about getting from start point to end point efficiently. The traveling salesman must visit all points exactly once and return to starting point, forming a round trip. Forming a round trip movement. And then lastly here for this, or this is 1.1 for, sorry. 1.1 dash 5. Okay, come up with a real world problem in which only the best solution will do. Then come up with one in which the solution that is approximately the best is good enough. Yeah. A real world problem in which only the best solution will do is are space travel computations, where rounding errors or miscalculations could result in dramatic issues or even death, right? I guess. A real world problem in which an estimate of the best solution is good enough could be it or is. What's an example where it's kind of good enough? What's an example if it's like kind of good enough? An approximation is kind of good enough. Anybody have any ideas of where an approximation is okay? What's something that we guess on in our daily life that's like okay? Interesting. Let me think about it for a second. Where an estimate is the best solution is good enough. I mean, I don't know. Let's go ahead and talk about it. A real problem in which an estimate is good enough could be something like delivery route planning. A quarry wants to minimize the travel. The perfect route will be computationally expensive and unnecessary. is driver routing, where the best route is where the say sure. A real-world problem which an estimate is for this is good enough is the delivery route planning for a local carrier service where small deviations from optimal route do not cause serious consequences. Is my space example good? Yes. Is it what exact best solution acceptable? Where best route is expensive and most likely a NP problem, NP complete. Would the delivery driver problem be NP complete? Is essentially is NP hard? It's expensive. And small usually, I don't know, how would you say this? I'm struggling with this guy. A real-world problem in which an estimate of the best solution is good enough is a delivery driver routing, where the best route is computationally expensive and small deviations are usually acceptable and don't cause serious consequences. I like that. Right. What is another example of one where the best is needed, like MySpace? Another example where the best solution is required could be in medical drug dosage calculations. Even small errors in dosage could have consequences. We'll say another example is medical drug dosage calculations for chemotherapies and anesthesia. Oop. I like that one. Airplane autopilot trajectory. Okay, we'll say we'll just do some like examples here, like so. My dog be barking. She's not happy about something. Okay, so we'll say space travel. We'll say medical drug dosage. We'll kind of make a list here. Medical drug dosage. And then we'll give one more I like that I think is cool. This is the airplane autopilot trajectory adjustments during maneuvers. Okay, I like that. Hey, Ashwin. Hey, you're inspiring me. I'm a first year undergraduate. Nice, dude. How's it going? My name's Michael. I'm 26. I have a degree in human biology and a minor in chemistry, and I work as a formulation chemist full time for a biotech company where I make and manufacture and formulate biotechnical or biological controls, which are used in patient diagnostics. Today, and I teach myself about every single day. I took a little break the past few days because my lady has been visiting me, but I teach myself pretty much every single day after my 9 to 5 job and on my weekends. Computer science and programming, where we build projects, read books, and take courses, teaching ourselves just as we would, back in college, but without the expense. So I am really good at holding myself accountable, and I'm really passionate about learning this stuff. So if you are too, then this is a great place to be for like daily studying and holding yourself accountable also to a similar degree, and also just hang out and chill and kind of remove the pressures of coding and just make it more fun and more enjoyable on a personal level. But we are reading Corman Introduction to Algorithms, which is a kind of Bible of algorithms and computer science for undergraduate students and graduates. So we are just finished chapter 1 today, and we're going over the just the in-text problems here, uh, just getting some practice with those. So let's keep on going here. We have a couple more exercises, and then we will. I'm going to post these notes on my GitHub so you can get access to them if you would like to follow along. And I'm also recording and be uploading this back to the channel for a watch along, read along kind of series as well that I do. That was just ChatGPT, just to get breakdown of some stuff and clear some confusions on stuff I'm reading, which helps a lot. Okay, so here are some exercises. Give an example of an application that requires algorithmic content at the application level and discuss the functions of the algorithms involved. Oh boy. We're stepping it up here. An example of an application that requires algorithmic content at the application level is at the application level. What, like a calculator? Or like or just like a GPS tool? Apple Maps? Yes, a GPS tool is a perfect example. Function of algorithms involved: the shortest path, traffic routing, alternative route is GPS routing like Apple or Google Maps. Some functions of the algorithms involved are finding the shortest path, alternative routing, traffic conditionals, right? Traffic conditionals, weather, traffic and weather conditionals, traffic or weather. Right, you have like geographical differences. Geographical/national differences. like laws and stuff, like driving laws, that's a solid answer. If you want to make it more precise, an example of an application that requires algorithmic content at the application level is GPS routing, such as Apple Maps or Google Maps. Functions of the algorithms involved include computing the shortest path, generating alternate routes, adjusting for traffic or weather conditions, and accounting for geographical or national road regulations. Yes, that is a good rephrase here. As long as it's like 99% along with the same lines I put, then I'm fine with copying the the more precise version. But I usually don't like to take things directly from this. I like to kind of generate my own thoughts, feed it into that, and then see if it has any suggestions or ideas. But I think the best way to approach it is to first generate your own ideas, right? Just for a learning purpose. Okay, suppose we're comparing implementations of insertion sort and merge sort on the same machine. For inputs of size n, insertion sort runs in a constant of 8 n squared steps, while merge sort runs in 64 n log n steps. For which values of n does the insertion sort beat merge sort? Okay, so this one we just need to pull up a graph. Desmos graphing calculator. This is just the Desmos calculator. Desmos graphing calculator. Cool. And so let's put in our functions here for n equals, we'll say 1 here, and then we'll say 8n squared. And then we are going to, or we'll say f of n equals to 8n squared. And then we have f of n equals to 64 n log n. But this is log base. How do you do a log base? There we go. Am I doing this right? Okay, so our green line am I doing this right? 64n log base 2 of n. I don't know if I'm doing this right. 64n log base 2 and 8n squared. Curious. Even, am I being dumb here? Or am I formatting off? Why is this graph? It should be like this, no? Well, it's not log. If it was log, it would be like that. If it was 64 log, it would just be skewed upwards, but it's still overall curved to the right. Yeah. And then if we have 64n log n, okay, so we still, okay, so it's just heavily skewed to the right. Okay, gotcha. Okay, so there's an inflection then, or an intersection, sorry, whatever you would say, at this point here. So that point is x 1.1 and y 9.6995. So for what sizes of n, so if n is our x values, would the insertion sort, which is this guy, beat so every value of I kind of want to break this down. I am graphing these right now, and I see an intersection at 1.1 and what was it? 9.68. Great, you're basically trying to solve for any inequality where insertion sort is faster. So you have it is less than this, so you say let's do is a transcendental equation. So exact algebra is easy. No. 1.1, 9.68 xy chord. This is insertion sort and takes a number of steps. For any n less than 1.1, insertion sort is slightly slower. Actually, check since insertion sort goes faster for n just below 1.1 is slightly slower. So then what would be like if I just paste in this? So simplify. 8n squared is less than 64n log n, right? Which is n squared, where we divided by 8 across, which reduces that down, and we get n. So divide by an n, divide by an n. Okay, that gets rid of that n. Okay, so now we have this. We don't intersect at 9.63. I'll look up let's see here. Other answers here. Okay, here we go. This is actually I want interest. I'm working on privately this, playing around with other properties of the log, I can further get this, or n is less than 2 to the power of n divided by 8. Since it doesn't take long for the 2 to the power of n divided by 8 to get larger than n, it would be reasonable to experiment to find roughly where this happens, using multiples of 8 to make this easy. That's just somewhere between 41 and 48. Huh. 43. And why is, when you graph it, do you get, when you graph these functions, okay, let's just see where the output then for n. So n is 50. Well, now we've gone 20,000 over 18,000. It's right there. About 43. So there, it's less than that one. And now it's greater. So about 43 to 43.6. About 43.2. 0.3, 0.4, 0.5, about 43.5. I got an answer of about 43.5. I don't know what it's doing. We'll say about 43.5. N equals about, so for what input size of n insertion sort, for what input size of n, for which values does insertion sort beat? For all values less than or equal to about 43.5. Right. So this merge sort, or this, sorry, insertion sort and merge sort here, this is insertion sort and merge sort, at about 43.5, 1, 2, 3, 4, 5, 6, 7. It's less than. It becomes greater than. It's not hard to show that. So then if we go to our Desmos graph, I wonder, like if we go to here, we say f of n is equal to this, we say f of n is equal to this, and we say n is equal to 43.5. We say x is equal to 43.5. Where do these points meet? It was like wasn't it 18,000? There. Here. 43.5. Okay. Nice. Okay. (1.2-3). What is the smallest value of n such the algorithm whose running time is 100n squared runs faster than the algorithm whose running time is 2 to the power of n on the same machine? Okay, so let's pull up the whiteboard. So we want to say, what is the running time of an algorithm whose running time runs fast now? So 2 to the power of n is less than 100 n squared, right? So divide this. So to reduce this down by 2 to the power of n. So we could divide by 2. That would just make it 1 to the power of n, which would be what? So this would be just 1. So if you divide by 2, this would give you just 1 to the power of n, which is just 1, which is less than 50 over n squared. Okay, so then let's see here. Let's go to Desmos. Let's plot 100n squared. And let's plot 2 power of n. Let me delete that. We type in x equals to 1. Zoom out here. Down. Zoom in here. It's x equals to 1 here. That's definitely not it. So they intersect here at y equals to 1. Sorry. Basically. Point 1 basically intersects here. So if I bring up my whiteboard, so I'm going to take this, I might go to my Stack Overflow. You want values of n where 0 times n squared is less than 2 times 2 to the power of n. First thing you have to know is the running time means that you're talking about theoretically the running time of the algorithm is the number of steps. Hmm. It's 15. Hmm. The smallest integer such that this is less than 2. Okay, so maybe I had this flipped. Whose running time is faster than an algorithm. Oh, so the number of steps is less than. Okay, so 100 n squared is less than 2 to the power of n, right? This has less steps. So if you divide by 100, that'll obviously take you to n squared is less than 1 over 50. Oh, no, so this would be, can you actually do that? I don't think you can. How did you reduce this? Hmm. Huh. Trying to figure this out. So how can we just solve? So saying and we just both transcend an equation that are both sideways solve it and make your trial and error with the table method, graphical method, plot. X equals to 0.1. So, okay, so let's see here. So if 100 n squared is equal to 2 n, that doesn't work. We get it. Am I trolling? No, that definitely is the right about. Okay, so what if we look at a larger point in time? These two graphs ever intersect. I'm curious how you would solve this. Okay. So for A to run faster than B, 100 n squared must be smaller than n squared, or 2 to the power of n. Intuitively realize that A, quadratic time complexity, run much faster than B, exponential complexity, for very large n values. Let's check that. From n equals 1, let's go all the way up for values of n where the powers are 2 to see what happens. So as we increase n from 1 to 16 and plug this in, we can see that it is true. Okay, we see that the the exponential function remains less than until we reach n equals 16. So now they fine tune even further to n equals 12 through 15, and you can see that it flips on n equals 15 here. So at n equals 15, A starts to run faster than B. It's 15. Interesting. Okay, right. So we'll say this is 15. N equals 15, and what I'm going to do is I'm also going to grab this. Cool. Okay. Determine the largest size, and it will probably be solved in time t, assuming that the algorithm. If f of n takes microseconds. Okay, got you. All right, you guys. Cool, cool, cool. Sweet. All right, you guys. That was chapter 1. I'll come back through and we'll do problem. I'll do number 1. I'm gonna do this one probably off stream to give myself some more practice. Probably in a few hours, just to solidify the information after I give myself some time to let it pass and marinate. But this was chapter 1 of Introduction to Algorithms by Corman. So really awesome book here to be diving into, and I'm super excited to be continuing on with this. We'll be continuing on with chapter 2 at a later date, probably over the next few days. We'll get into chapter 2. It's getting started. So chapter 2 runs from page 16 to kind of a long one here. 40-ish with including the problems, so 16 to 30-ish, 30, 40, 38, 36, 37. Yeah, 36 to 16 to 37. All right, you guys. I appreciate you guys being here and joining me today. I will go ahead and upload this to the channel for the watch along and read along series, where I can learn and teach myself computer science, and you can learn right alongside me. Thanks so much for being here, and I appreciate you for joining me. This was chapter 1 of Introduction to Algorithms by Corman. Um, Thank you guys so much for being here, and we'll continue on in the next one. If you guys would like access to my notes, please find that in the GitHub linked down below, and I'll see you guys tomorrow, or maybe even later tonight. Bye, guys. Bye.